my pleasure to be here today, I enjoy teaching. In fact, it's funny that he chose to mention this. I thought I'd start, and it's sort of a disease. The reason I've written so many books and had the opportunity to work on so many book projects has been that I really enjoy teaching. So this is really an encouragement to interrupt me and ask questions. If we don't get through all the slides that I have in each of the sessions, and yes, the next 3 sessions apparently I will be talking. If you don't interrupt me, you won't get as much out of it, but feel free to ask questions. I think some of the things that have already been talked about, I'll have the opportunity to speak to. I have worked at Intel for 27 years. I thought it'd be a cool place to go work for a few years, go find another job. I've been very fortunate. I work with a lot of very smart people, and I don't believe in what Intel's doing because I work there. I still work there because I believe in what we're doing. So if my passion comes through for some of our products, hopefully you'll forgive me a little, but ask me about the trends and so forth, because I'm not here to plug one technology or another. When I started my career in parallel computing, I worked on systolic array processors. And systolic array processors were all the rage in the late 80s because clock rates weren't going up. One of the darndest things about VLSI was that we could not get the clock rates to go up. So processors were all just kept hovering at 2 or 4 megahertz, and everybody knew parallelism was the future. Well, we were a little ahead of our time. Clock rates took off. The parallel processing projects I was working on at the time died out because things like Pentiums went from a handful of megahertz to over 100, and then we kept ramping clock rates. That eventually ended, and here we are again. Parallelism's important, and this time I think it's pretty permanent. But I've been in HPC the whole time. One of the things that really surprises me, though, is the last 2 book projects I've worked on. See, I got smarter. I wrote the first few books myself. The book that just came out this week, I had 73 people work on the book. I was the lead editor. The book before that, only 69 of us. It's a little easier to write a 500-page book when you have so much help. I had the opportunity with both of these books work with the most incredible people around the world on what they could do for parallelism. In the first book, the former CTO of CERN wrote a foreword for it, and that was exciting enough. But then I have all these chapters written by people around the world. And one of the chapters written by CEA, by some folks at CEA, was on a very important application that they use. And they got 12x from where they started on a Xeon Phi. I thought, that's pretty cool. They were one of the chapter authors that didn't want to show me the results on Xeon, and you'd think that was because it was embarrassing. It was 5x on Xeon from where they started on a real app that they used all the time. And my reaction to that was, good grief, you could have bought a system a fifth the size or done 5 times the science if you had done this work earlier. And all they did was parallel computing work. I say all they did. This is my sense of humor. It was hard work. An OpenMP directive here, a little bit of rearranging a data structure here, but all basic things that over the next couple of weeks, hopefully you see what the basics are. And attending to those basics mean that your program will run on future architectures more and more. You have to be careful. There's always the temptation to do something for today's hardware, and you probably will. You should. Take advantage of it. But if you do too much stuff that's tied to the way the hardware is today and won't be tomorrow, that's a problem. Well, all the changes they made applied to Xeon and Xeon Phi. They were very generic changes, and yet they got 5x on Xeon. And the authors, the explanation I got from them, and I got time and time again, was, 4, 8 cores wasn't that interesting, but 61, that was interesting, so we thought we'd go work on parallelism. I've heard this over and over again. You'll see the same thing with the GPUs. My goodness, why are we seeing people so excited about GPUs? Well, the opportunity for 100x, whether it's there or not, the opportunity for 100x is much more exciting than me giving you a dual core and saying you might get 2x on the kernel deep in your program. So 61 cores. So this massive amount of parallelism is very, very inspirational. And so I often summarize it as inspired by 61 cores. And I got to see this over and over again. So it's really exciting to me to talk about parallel computing and hope that some of that excitement comes across. Computer architecture is really fun again. This is kind of the summary to my first talk today and I'll walk you through some of how I think about computer architecture and where it's going, and some of the things that come together. But more than anything, the trend I think that's really important is to pay attention to how do we do this without making software the victim. Now, I'm first and foremost a software developer. I've worked on many, many software projects over the years, but I've always been very tightly associated with hardware. Since the systolic array days, I was one of the architects on ASCII Red, the first teraflops computer in the world, and I'm fortunate to be working on Xeon Phi projects these days. Hardware is not getting simpler. You heard things just in the last talk about networks and network integration and so forth, and it's really exciting, but at the end of the day, we want to make sure the software still works. So, all these complicated things about making the network controllers more and more complex and then integrating them on package or on die, you know what? Hopefully it still supports the protocols we want, like MPI and PGAS. That's the goal. But it just drives down the latencies and increases the bandwidth, hopefully. Same thing with these computing devices. We've got processors, we've got coprocessors, we've got GPUs, we've got FPGAs, and we'll have more variations of these, and there'll be other surprises that show up over time, I think. What if we view the world this way? And this isn't because I'm some guy from Intel that loves processors. At the end of the day, somebody has to step you through the logic and be in charge. So we've always called that a central processing unit, a CPU. And we've always had things hanging off of CPUs. Over the years, many, many different things have hung off CPUs. So today we've got coprocessors, GPUs, FPGAs. But at the end of the day, something's controlling or stepping through our logic, and something might be helping accelerate it. I've had many, many accelerators over the years. So this is kind of, to me, if you think of it this way, why not? Let's have something that's making our computer, a CPU. It may or may not be really powerful, and then we'll have something that accelerates it, and those may or may not be present or powerful. Even if you look at the world that simply, there's just so many exciting things going on now. Memory hierarchy is one of the more exciting areas. It's going to get more complex and more sophisticated and so on, and you've just got to ask the question, why? What benefit are we getting for software, and how should I view it? Locality is just incredibly important. And then there's many other issues that you're going to hear about all week. And the darndest one is power consumption, because if we could just ignore power consumption, we could just focus on performance exclusively. But there's a lot of trade-offs, and so you see a lot of things in designs these days that are hard to understand if you don't understand what the designers are looking at trying to help with power. The same thing, unfortunately, is true of the way we design software, too, is the software things will affect us. One huge one is this concept of doing more computation and less communication. I've spent most of my career being really proud if I could take a loop and reduce the number of instructions in the loop. That's not the way the world is anymore. That's all we used to do. Nowadays, if you can come up with an algorithm that moves data around less, whether it moves it around in local memory with your nearest neighbor or across the fabric, if you can move around data less, there's a really, really good chance that your program will be faster than if you do that. And there is so much opportunity for that yet. As I work with applications in the industry and look at it, this is a new thought. And new thoughts don't take over the industry all at once. They're more on the order of a decade, at least. And so we're in just the beginning stages of really re-examining applications, algorithms, and redoing them to minimize communication rather than computation. But forest. There's an old cliche about people missing the big picture because they don't see the forest for the trees. You see trees everywhere. Now, I love computer architecture. We could talk all day about computer architecture, draw diagrams, show how we can connect buses together, how we can make things work really well. But a question that really fascinates me is, can we teach parallel computing without teaching computer architecture? Now, this is on purpose a provocative question. And I worked on a project with Michael McCool, who founded RapidMind, and Arch Robson, who was the architect of Intel threading building blocks of TBB, on a book called Structured Parallel Programming. And it's gotten some usage in universities. There's some really cool material we have online that some universities have developed in teaching. But the reason we did this book was we tried to think, what are really the fundamentals of parallel programming at a kind of an abstract level. Not teach MPI or teach OpenMP or teach TBB, not teach the language. And also don't teach computer architecture as much as you can avoid it. Now, again, remember, I love computer architecture. I cache protocols. I got going, the simple idea that cache protocols are messy, the cache protocols have gotten really complicated. It's really fun. But can we learn computer programming without having to know computer architecture? How much can you take it out? We teach people Java and send them off to be Java programmers, which is, by the way, a disease because they don't know how the machine works at all. But we teach programming languages without starting by teaching how a machine is built. We don't start teaching students how to program by teaching them how the insides of a computer work. But we tend to do that with parallel computing a lot. Way too much, in my opinion. Now, we need to come back. You need to understand motivations of locality and so on. But can we motivate locality as a computer science thing, a goodness of how you design your algorithm, without teaching you cache protocols and cache hierarchies? And I think we need to move more towards that. I actually had a stack of books. I set them at home. It was about this tall of computer programming books. And then I went through each one and tried to count how many pages were actually teaching computer architectures and how many were teaching programming, even though books said they were about programming. And I don't remember the statistic exactly, but it was something on the order of 70% of the page counts were dedicated to computer architecture. And that just frightened me. And that's the way I tend to teach. So anyways, I try to boil it down. There's all sorts of things. We've got, I'll talk about, and I will talk more about cores and hardware threads and hyper-threading versus multi-threading and all sorts of things, vectors and offloads and heterogeneous computing design, integration of networking, clouds and caches and NUMA and all this. And that's good. It's good that you're interested. It's good that you should learn about these and so on. But the question is, can you abstract that and understand what your mission is when you're actually writing software? And I like to make things as simple as possible, and then I'll make them complicated, build on that. It all comes down to exposing parallelism and paying attention to locality. Now, I've way generalized this. Because parallelism, in order to get scaling or get performance, you might need to do vectorization. In order to get scaling, you're going to have to pay attention to locks, not moving data around too much, all of these things. I lumped a lot into that. And locality of reference, the ability to understand how much moving your data around. I think you can boil it down and try to pay attention to these two. And that's really our jobs as programmers, increasing how much parallelism we can expose in our applications and our algorithms, and then how much we can increase locality of reference. And this is really, to me, these are the universal things. If what you're doing to your application is exposing more parallelism, finding ways to expose nested parallelism, finding ways to expose parallelism in your algorithm, create more threads. This is it used to be it was easy if you could just figure out how to make your program run in 2 threads. This is great, parallelism, or 4 threads. Now we've got machines the top machines in the world, number one machine, I don't remember exactly how many, is it 3 million cores, the machine in China. That's a lot of cores across the whole machine. That's a lot of parallelism. So the trend continues. The idea is, the programs that are going to scale to that magnitude need to expose a lot of parallelism. You need to give the machine the opportunity to run in parallel. So if your application's really written in a way that can't expose it, you've got a problem. And locality of reference. These are permanent things. If you can expose more parallelism in a generic enough fashion, you'll be able to use any computer of the future. And if you can pay attention to your algorithm design and keep your locality of reference and your independent, the great thing is you want locality of reference, but you want the references to be as independent as possible, because that gives you the parallelism. The more, it's great if you can just use map and solve your whole problem, you're in great shape. It's the darn interactions between those things that causes a problem. Anyways, this is the mission, I think, of us as parallel programmers. And so let me back up a little. I don't want to assume that everything is intuitive. And some of these things how intuitive are they? I don't know. It'll probably vary in the room. One question is, why on earth are we doing multi-core and many-core and so forth? And actually, this is about a 10-year-old thing, so you probably heard processors aren't unicore anymore. This is a graph that I keep updating. It's a plot of every processor essentially Intel's ever produced that does x86. I actually have data on Spark and Power and things like that and AMD processors, but it kind of blurs the lines because there's different offsets. The question is, the technologies and the instruction set you're implementing get different, and I finally gave up and just said, I'll just do x86, because at least the trend is obvious. The trends are the same for all the different processing devices. It just skews the lines a little. But this is a clock rate thing. And boy, we were on a rip for a long time. And then somewhere around 2005, boom, clock rate stopped. And this is pretty amazing problem. And it happened for a variety of reasons, and it's not going away. But one of the interesting phenomena is that Moore's Law, which is, we were just celebrating its 50th anniversary, Moore's Law continues. And yes, there's lots of articles about the upcoming impending death of Moore's Law and so forth. Those are always there. I've been reading those for at least 15 or 20 years now. There's a lot of energy behind the concept we keep making things more and more dense. And the Moore's Law is about the fact that we've been able to, for a long time, double the number of transistors that fit in a given area in about every 18 or 24 months. And some people say, well, maybe that's slowing a little and this and that. But this is a pretty big deal, to be able to double the amount of logic that you can throw at a problem every couple of years. This is a pretty big force in our industry, and things like talking about integrating NIC chips and so forth all comes from the fact that we can keep putting more and more transistors. It's not always obvious what to do with those transistors, but the trend continues. And of course, it wouldn't be an Intel talk if somebody didn't mention Moore's Law, so it's almost mandatory. So what's been happening with these transistors, a very large amount, is increasing the number of threads and or cores that the computing device has in it. This is true even on things like GPUs, right? It's not just a CPU thing. So any computing device has been following this trend. And the amount of data that you compute at one time, in the case of Intel, this is things like going from MMX to SSE to AVX to AVX 512. The width of our computations, fundamental computations, go up. So not only can we do more things in parallel with cores and threads, but we can operate on more data at one time by expanding the width. This all comes from just looking at, oh my goodness, I've got all these transistors, what am I going to do with them? And parallelism is a pretty obvious way to expand. And to the, there was a great question in the back about, whether you get away from mainstream. One of the things that's great about parallelism is we have a lot of the ability to take a basic design and build different versions of it. We could sell you an 8-core or a 16-core device, or we can sell devices with and without AVX512. We can swap things in and out. The design stays the same, but we get a lot of variety out of this. So parallelism is very attractive that way, in that we can build different devices for different markets by varying the amount of silicon we dedicate to this. And you'll see this with some of our processors for desktops and laptops, mobile devices. Some of them, much more of the silicon is dedicated to the GPU than to the CPU on some of our devices. In HPC, that's not true, but in some of our markets, the GPU dominates our dies these days over the CPU, because we're able to throw more parallelism at that, and people are looking for that realistic experience that you get with your graphics processing. So this was supposed to be an architecture talk, so let me see if I can go back. Really quick history of the world, according to James. CPUs used to have CPUs in memory. Those were simple. Somewhere along the line, the memories got slow enough that we put caches in between. Yes, there was a time when there were no caches. That was really easy to understand the instruction timing of my programs. The caches get more and more complex, more and more caches. Eventually, you suck the caches onto the die because that lowers latency, increased bandwidth to the core, and so forth. Along come floating point units. Sometimes I make the observation, software has had the ability to handle floating point for a long, long time. Hardware hasn't. So when people tell me, oh, a language shouldn't have features the hardware can't do in it, it doesn't resonate with me real well, because I grew up on computers that didn't have floating point in hardware, but I used floating point in my programs written in BASIC or in Fortran. And so eventually that gets integrated too. And then we've got other things coming along, like GPUs. GPUs come along in parallel. They grow up alongside with us integrating caches and floating point. And it's kind of inevitable. We'll take and integrate the GPUs onto the die. That's been done for a while. And then along come things like Xeon Phi many-core coprocessors, and we've demonstrated some of our new Knights landings, which will start shipping before the end of the year. And we've got a many-core CPU integrated on a die. And then you've got network fabrics, you've got nodes. So we've got tons of variety, but you notice a trend here is integration. There's a lot of benefits of integration. Of course, one of the things that holds us back on integration, one thing is die size, just do we have enough transistors, but Moore's law keeps solving that for us over time. The other one is how general purpose is it? How much are we able to take it on and off? And just not a product announcement or anything, but Intel is pretty interested in FPGAs. You may have read some news about an acquisition that we're in the early stages of trying to have happen. But we've been working closely with FPGA vendors a long time. FPGAs ultimately are about reconfigurability. So just think about how much fun it would be if that reconfigurability got integrated as well, and what you might be able to do to keep general purpose. A lot of fun in the future. So clusters are made up of hooking all of these cool things together. Yes, we'll integrate NICs. All of this stuff is very cool architecture, very cool trends, integration, 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 and it's going to continue. What can you think of that we could integrate more? The job for us as programmers stays the same. Let's expose parallelism for this highly integrated device, and let's pay attention to locality so we're not making the device work too much, just shuffling data around needlessly. Now, who can tell me what Amdahl's law is? Who could summarize it quickly? Put the class on the spot. Okay, everybody's thinking this is a dumb question. We all know Amdahl's law. Who wants to tell me what it is, though? Wow. All right. We can't have 2 weeks of parallel programming class and have an entire class unable to tell us what Amdahl's law is. So let me tell you how I like to describe Amdahl's law and Gustafson's observations on it. Now, I stopped short of calling it Gustafson's law, just because I think when people say that there's two laws and that they're opposing, you think, gosh, which one should I pick? They're the same thing. Let me show you why. Let me take a really dumb program. This program takes 500 seconds to execute. It's made up of 5 things I want to do. They each take 100 seconds. Well, I'm pretty smart. I'm able to get 2 parts of it to run in parallel on my dual core. Perfect scalability, too. It's really awesome. So now my program is running on 2 cores, and it only takes 400 seconds to operate. This represents a 25% speedup, a 1.25x speedup. Now, if I get on a quad core, have perfect scaling, I can get a 1.4x speedup. In fact, if I get massively parallel so that I squeeze those 2 regions down to 0, I get a whole 1.7x speedup. Now, this is rather unsatisfying because I've just taken a computer that's infinitely parallel, and my parallel program only runs 70% faster. So Amdahl, being a very smart guy, back in 1967, basically said, you're going to be very frustrated trying to speed up your program if you can only speed up parts of it. You're going to be frustrated by the serial parts. The serial parts would be these 300s that didn't move. And so for a long time, people held this up as evidence of why massively parallel computing would never work. Of course, I started my career working in massively parallel computing, and I didn't understand all these people quoting Amdahl's law and saying that that meant we would fail. And there were great people like Seymour Cray who spoke out against massive parallelism because it'd never work. Amdahl's law was the reason. So what did we get wrong? Well, it's kind of embarrassing. It wasn't until 1988 that someone spoke up loud enough to get their name plastered onto a law. John spoke up and said, hey, you know what? Maybe we ought to pay attention to scaling problems, not just trying to take the program that's been sitting around since the 1950s and make it run faster and faster. So here's how to look at the same problem. What if I have this program, but as I scale it, instead of trying to make the same amount of processing happen faster, what if I got the right program and the parallel regions actually are where I'm processing all my data, so I'll throw more data at it. So instead of squeezing these regions down to run faster, I'm actually giving them more data. So here I've got 700 units of work going on my dual core, and I've got a 1.4x speed up. If you remember, my dual core only gave me a 1.25 when I went the Amdahl's law. All I was doing with Amdahl was speeding up the same problem. Now I'm cheating in a way. I'm speeding up a bigger problem. If I continue this, I've got a 2.2x speed up on a quad core. This is awesome. And, it keeps speeding up forever. Of course, this is rather idealized. I'm, really happy that I have perfect scaling here. But the concept is, to me, is the parallelism's in the data. And this is really, really important to understand. If you can't scale your problem, you're going to have challenges. Now, in the industry, for some reason, we came up with these terms, strong scaling and weak scaling. So this is called weak scaling when you make the data bigger. Get over it. This is where the parallelism is in data. So if you're looking for parallelism, if you can find it in your data, it's, in my experience, generally a lot easier to understand what your job is. So Amdahl's law said you could be very frustrated by the serial parts of your program, but it's very much from a perspective of the if you're just trying to take the same problem and make it faster and faster, and you're going to do some of that. Gustafson's observations on the same phenomenon basically say if you can scale your problem up, you have a better shot at using the parallelism. And so, to make either of them work, or to make the Gustafson's work, the serial parts need to not be where you're processing your data. So I guess that's the hard part in what I just showed. So, Xeon Phi. Xeon Phi is pretty personal for me in a kind of a funny way. I was one of the architects on the world's first machine that could do 1 trillion computations a second, ASCII read, installed in Sandia in '97. In '96, we were able to have about 2/3 of the machine built, and we went over 1 teraflops. Much to my horror, in 2011, I was handed a chip that I got to hold in my hand and was told, actually it happened the year before that, but and was told, now I'm holding 1 teraflop in my hand. ASCII read, just to be clear, would have filled this room, and it consumed 850 kilowatts of power. The chip I was holding consumed about 200 watts of power and did the same amount of computation. That's the industry we're in. Well, it gets better. We upgraded ASCII read to be a 3 teraflops machine by swapping out all the processors and popping in the next generation that we had specially packaged. We never sold those, but we specially packaged them to plug back into the system. I think it was the first massive example of re-upping a machine to stay on the top 500 list longer. That wasn't exactly our motivation. Of course, we wanted our customer to be happy, but it had the effect of keeping us on the top of the 500 list for top 500 list for longer. But we got over 3 teraflops. Knight's Landing, which is our 2nd generation Xeon Phi, is over 3 teraflops on a chip. So it continues, and I get to hold those in my hand too. Only the broken ones. I'm not allowed to touch the ones that work right now. But it's exciting. It's exciting to see, but this is early in my career getting to work on ASCII read, and later in my career, not late in my career, later in my career working on Knight's Landing. This is exciting, and it's just going to continue. But why on earth did we... What's that?
How many cores would it be in that 3 teraflop processor?
So the ASCII read was about 9,600 processors, each one of them with 1 core. Half of them did communication, purely sped up the precursor to MPI, basically, and the other half did computation.
But that 2015 Knight's Landing one, how much?
Oh, the Knight's Landing?
Yeah.
It has 72 cores. And I can say that out loud now because we finally made that public. It's been a rumor for a long time, but yeah, 72 cores. So Knight's Corner has up to 61, Knight's Landing has up to 72 cores. Yeah, pretty amazing difference between 9,600 and 61 or 72. Yeah. So why did we do Xeon and Xeon Phi? This is to me, this is the fun part of architecture. It's a classic question. Should I build a machine with a bunch of big cores that can do anything? They're kind of power hungry, kind of generic, versatile and all this. Or should I build a lot of smaller ones? And this has been going on a long time. Go Google thinking machines, and those folks, and the work they did in the 80s on seeing bit slice processors. They hooked a bunch of bit slice processors. They went way too far. The processors were underpowered, but there were lots of them. But it really was a great experience to look at in terms of, you should trade these things off. Bigger isn't always better. And the question here is, what can you do? Now, just to, you could go really crazy like GPUs do, and I colored it green, in deference to good friends over in NVIDIA land. But Intel's got GPUs as well. In fact, we make more of them than anybody. Same phenomenon. Specialize, make them smaller. Now, the thing about a GPU or these things is some of their ability to get so much parallelism is by being more restrictive. So there's a scale of restrictiveness. GPUs cannot do everything a CPU can. Now, that's not an absolute, gee, that's terrible and this is good statement. It's an engineering trade-off. So what restrictions can you live with? Now, this massive amount of parallelism that we can build into an architecture today is a lot of fun to look at, and how restrictive it is another. But I can't resist thinking of Seymour Cray and how much he didn't like this. He didn't like the idea of massive parallelism so much, he once gave a talk, and he's very famous for saying, now remember, he's from Minnesota, middle of America, farmland. He'd say, would you rather plow your field with 2 strong oxen or 1,024 chickens? I've always loved this quote, because it was a really biased quote, because it's like, everyone laughs at the idea of plowing, with chickens. So he was kind of biased towards the more parallel. I'm not as biased. As an engineer, the challenges of which you should pick is a very complex, and there's a lot of relationships. Now, with Xeon Phi, what we decided to do was, instead of building general purpose Xeon type cores, we wanted to put a lot more cores on, so we had to do one thing. We had to assume the program you were going to run on it was parallel. And that's a huge decision. And it frees up a number of design things. We don't have to worry, we don't worry as much about a lot of things Xeon tries to do to make serial programs run fast. We just don't care. If you've got a serial program and you run it in Xeon Phi, I can tell you how it's going to run. Terrible. Absolutely terrible. Same thing on a GPU. They're not about serial program performance, and yet Xeon, our mass market processors, are. But we decided to do something different than other column accelerators, and that was we wanted to preserve the same programming models. Now, I think what we did is amazing and wonderful. But I don't want you to walk away thinking, oh gosh, the Intel guy thought this was amazing, the NVIDIA guy thought this was amazing, the IBM. These are engineering trade-offs when we do designs. And Xeon Phi, our design trade-off is we want to preserve all the same programming models and languages and tools and run the same binaries, starting with Knight's Landing, but assume that a parallel program is running on us. How can we design differently because of that? And that's what makes Xeon Phi different than Xeon. That's the only thing we're trying to do with our design teams, is say the Xeon Phi team has the liberty of assuming the only thing that's going to be run on it is a parallel program. And so we want to make sure that programs can span these two. And that's what we're up to. Now, the cores, each core is less powerful than a Xeon. And so you end up with graphs like this. After I was teaching Xeon Phi for a while, I finally drew this graph. And it turned out to be incredibly important as I taught these classes, sometimes week-long classes on Xeon Phi programming, because the Xeon Phi programming was parallel programming class. That's all it was, because we didn't break anything. We didn't have to teach. In fact, people would say, how do I do OpenMP infinity? And I would say OpenMP, underscore whatever affinity. I'm not very good at remembering the names, but I pull up the slide. And they'd say, that's the same as it is on Xeon. I said, yes, exactly. We said we were going to preserve the same models. But it takes more parallelism being exposed to get equivalent performance. A Xeon's performance on, say, 10 threads is up here, whereas Xeon Phi is down here. Same thing's true if you go to a GPU. Your benefit is that if you can expose more parallelism, you can get to much higher performance levels than you can on a Xeon processor. However, you have to expose the parallelism. Remember the part where I said our job is to expose parallelism? If you expose the parallelism, we can give you devices to take advantage of it. But if you can't expose the parallelism, you're better off on a Xeon processor than on a Xeon Phi. So people would show up to class with a program that was perfectly written to take advantage of 8 threads on a device that can handle 244, and go back to Xeon. You have to expose a lot more parallelism. This is a consistent trend we'll see in hardware, is that the hardware can take advantage of the parallelism if we can express it. So just to recap, so Xeon Phi has got up to 61 cores, bunch of memory. It runs Linux. I actually log in it. I like to show this. I log into it, and I can do LS, and I can surf the web on it. I can do all this is while I'm running on the card. And then we get Xeon Phi, Knight's Landing, and it takes it further. We go to 14 nanometer process. We're able to be a standalone CPU, whereas the first Xeon Phi could only be a coprocessor, up to 72 cores. They're Silvermont based, which may or may not mean something to you, but it means it has out-of-order instruction executions, probably one of the more critical things. 512-bit wide SIMD capabilities, on-package high-bandwidth memory. Here, I'll help you with a decoder. Intel people try to be very, very precise. We try. We aren't always. There's a difference between on-package and on-die. And when we say on-package, you can assume that means, oh, Intel just started talking about a multi-chip module where they'll put multiple chips in the same package and wire them together. On-die means it's on the same piece of silicon. So it's on-package memory. Very, very cool. Has some enormous benefits to have it there. And I didn't say it was faster memory. I said it was high bandwidth. It's close memory that's high bandwidth. It actually, performance-wise, you should be thinking the performance is the same as main memory. That's close enough. I'm not actually allowed to tell you the exact parameters, but when you should never have heard an Intel person claim this was faster memory. It's high bandwidth memory, and that's incredibly important to applications. That it's the same as caches are high bandwidth. Caches tend to be higher performance and high bandwidth. This is high bandwidth. And then finally, there'll be integrated on-package NICs. And did you notice I said on-package again? And this is actually an answer to the question before. Yes, we're taking it a step at a time. Integrating a NIC onto the same die would be a much stronger commitment than on-package. And we will get to be on-die. But by being on-package, you can either have that chip in your module wired in or not. You get your choice.
Probably worthwhile just saying a second what the difference between on-die and on-package is for everyone.
Sure. So a die is a piece of silicon. So when we manufacture processors, GPUs, whatever is made in semiconductor material, I almost said silicon, but I guess there are other semiconductors. They just aren't that important. Silicon, we do wafers, and each one of them has the part is called a die. The part that we eventually cut out and put into your package is a die. It's a piece of silicon, and on it we've drawn transistors and hooked them together. It turns out that the package that if you open up your computer, or if you ever put a computer together, you buy a CPU from Intel and you stick it into a socket. That's what I call a package. Now, if you pry the lid off the package, you might be surprised to find that some of them have one die in them, but some have two or three. And so when I say on package, it means that it's in that package, the thing that you actually would hold if you were plugging it into the computer. But when you pry it open, the die is a piece of silicon. And so on package, in the case of Knight's Landing, the most sophisticated Knight's Landing will have a die that has 72 cores on it. There'll be another die, or kind of it gets a little more complicated than that, but that's memory. And then another die that would be the NIC, and they're all hooked together in the package. And being on package has some enormous benefits, but not quite as many benefits as being on die. On die gives you your signaling, it can be faster, but on package it can be faster too, because when you go off package, you have issues with electrical issues. There's parasitic capacitance. There's a lot of issues driving a signal. Off package is harder than inside the package. So you can have higher signal rise and fall times inside the package than you can when you go off the package. It's even higher if you're on the die.
More like a motherboard? Package is more like a motherboard?
Well, a motherboard is even one more level out. So if you, a motherboard, like, if we were to pry open a laptop, I won't do that to your laptop, don't worry. It's really cool to do, though. I take mine apart several times. The motherboard has multiple packages or parts plugged into it. So the motherboard's one level out. So, computers are usually made up of, they can be made up of a bunch of cards plugged together. Each card or motherboard then has multiple parts on it. And the trend has been to integrate most of the sophisticated logic onto a very small set of chips that's on the motherboard. You'll have the memory connection, the chips that help facilitate talking to the memory, the processors themselves, the NIC chips. But then when you look inside the chip, you may have, I should quit calling that. I try to call them packages. We used to call them just chips, but then a chip is a slang term for a die. So since we're doing multiple die on one package, I need to call it a package and not a chip anymore. But I'll slip on that a lot. Let me finish up here because I know even though I started a little late, I shouldn't make us even later. Say a few things about patterns. So I was saying before with structured parallel programming, this book that I worked on, that we tried to think, gee, can we teach computer programming without teaching computer architecture? And I think the answer ultimately is patterns. Now, patterns have a very bad name in the computer industry to a lot of people because people get really excited about patterns. And one of them is a good friend of mine named Tim Mattson. He's written a nice book about this thick, Put You to Sleep. They get really excited about showing you every pattern possible, trying to build a whole well-thought-out hierarchy of patterns. And my being very much an engineer, not a researcher, not a computer science researcher, I want to know which ones work. Which ones should I use? So I think structured parallel programming, we focused on the ones that work. And I'll leave out the other 90% that were just there to make the hierarchy complete. What it is, it's about learning from people who have come before us. So, there used to be these Knuth books, there still are, that were real Bibles to me when I started studying, show me how to do sorts and how to do lists and introduce advanced concepts like that. Well, nowadays, it's really important to understand certain patterns that people have figured out how to make work well in parallel. And I would really encourage you to study patterns a little. And of course, the book that we worked on, I think, is a good place to look because we focused on patterns that work. But look, the patterns aren't that complicated. You know some of them already, hopefully, like map. Map is really simple. I've got some data. What if I could make it so that what I wanted to do to that data was completely localized to that data? So if I've got 1 million items in an array and all I want to do is add 1 to each one, I could apply 1 million processors to that, totally independent, boom, 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 boom. That's what this diagram is. Each one of those little blue boxes is add 1. So we take the data, we add 1, we put it back. There's no crossover, no dependencies, nothing like that. This is an incredibly important concept. In fact, people would say Google is founded and very rich because they paid a lot of attention to map. Their algorithms, they pay a lot of attention to scalability. They want to touch the entire internet and process it. And when you do queries and stuff, they really focus on making sure that they have massive amounts of parallelism they can throw at things and not data dependencies between them. So map is good. And then, of course, reduce. So Google's probably a map reduce company. Reduce, what is reduce? Reduce is, gee, after I've done the map, or after I've got my data in an array, probably maybe after I did a map or some other function, I want to summarize it. Like I want to add them all together, or I want to find the maximum value, or something of that sort. This is a very common operation, and again, people know how to make reduce happen in parallel, or how to make it. You don't just linearly walk and add them. You do it using a binary tree. But there are more. Stencils. Stencils was almost buried in our book as a sub chapter until I noticed in our outline that that's where it was, because that was a very pattern sort of hierarchy. I said, look, stencils are incredibly important. If you don't know what a stencil operation is, and you don't know about ghost patterns or halos around it, and how you can make them bigger and smaller to increase and decrease the amount of communication, you should study stencils a little. Because if a stencil will solve your problem, you're probably better off going and looking at stencils and abstracting your program to sit on top of a stencil. So stencils are a chapter in our book. We talk about stencils and methods of parallelizing them and what's available. Again, if you're trying to make your programs last forever, if you can write them in terms of patterns, you benefit in 2 ways. One, you get all this research that's gone before you on how to make them run in parallel. And the other is you can talk to someone else that knows patterns about what you're doing. Often I'll be talking to people and they'll say, oh, well, I'm solving it with a stencil, basically. And I go, oh, okay, I know what a stencil is. Pipelines. Sometimes people think pipelines can't be done in parallel or that they aren't as scalable. The reality is they are, because the little blue boxes often have parallelism in it, and that's nested parallelism. And I'll probably talk about nested parallelism after the break. But pipelines are really important anyways. We've done a lot with this, with structured parallel programming. I think pattern should not be a bad word in the industry, despite, now I'm doing that a little tongue-in-cheek, but if you really, really study patterns, that's a whole discipline unto itself. And there's conferences on it and all that stuff. And really, I just want to figure out which ones work and use them. That's my bias. And so, I go over to Tim and ask him which ones are good, and then after an hour of sitting in his office, I might learn something. And I go take that one pattern, and he's horrified that I don't want to look at the other 500 beautiful patterns. I just want to use the ones that work. So I think there's a lot of work to be done in this area still to really understand and generalize patterns. It's very similar, it's somewhat related to the dwarf sort of thinking from Berkeley, or they don't call them dwarves anymore, whatever they call them, motifs or whatever. But the idea of finding what have other people done that worked in expressing a parallel program. So in summary, computer architecture is fun again. Let's just make sure software is not the collateral damage. So walk through a bunch of different concepts. Hopefully it's interesting. I'd be happy to take a question or two before the break if there's time. And then we'll talk some more after the break.
Do you want to say anything about new materials, gallium arsenide or otherwise, how Intel is moving towards that, or is it seriously moving towards it? Is it just kind of waiting out on what's happening? Just to get an impression.
All right, so the question was, what about gallium arsenide? I said I've worked for Intel 27 years. Before I worked for Intel, one of my best friends in college, his specialty was gallium arsenide, and he went off to work at IBM and hasn't worked on gallium arsenide his whole career either. It's not my area of expertise. Silicon has pretty consistently proven to be very manufacturable and very in high volume, and problems keep getting solved on it. Intel's not wed to any particular semiconductor material, but the practicalities are that silicon keeps proving itself as something that works, that's been reliable and dependable. The world did change for us a number of years ago when we moved away from silicon dioxide gates to hafnium-based gates. And I think some people don't understand how revolutionary that was, but that was silicon had one big problem with silicon is that the manufacturing ways that we manufactured it, most of the electricity that we put in, most of the power, was just leaking out into the substrate and disappearing. And if that doesn't make complete sense, let me see if I can. You start with a layer of pure silicon and then we dope it, which is kind of a way of crudely of making transistors on top of the silicon, the pure silicon. And the idea is that the current's supposed to flow through the things we've doped and the wires we put on top, which have been either aluminum or copper through history. But some of it leaks down into that pure silicon, and it's just useless. Any current that goes there is useless. Well, there have been a few things that have happened to silicon. One is using hafnium-based gates. Hafnium is an element. I had never really paid attention to that element on the periodic table, but it turns out to have changed everything in silicon. The other thing is that people figured out that air doesn't conduct electricity as well as silicon, so instead of laying the transistors flat on the silicon, we've turned them up. That creates all sorts of problems, but the good news is that your gates are surrounded by air. These are called FinFETs. A fin like a fin on a shark, and FET meaning field effect transistors, which are the type of transistors we tend to use. But so silicon keeps marching on, and gallium arsenide and others have not been able to find their way into it. But we'll see. The thing that I think is that everyone's searching for is, can we get to optics? Can we get to practical gating of optics? And I think if we could figure out how to do that on any material completely, that would be a pretty big driver. I'm not predicting gallium arsenide's better than silicon, but there have been people poking around at that. So I guess that a firm prediction is I don't see it changing from silicon. I don't think anybody seriously does at this point, but you need to keep your eyes open and see what can go. I don't think anyone, when I started at Intel, I don't think anyone seriously thought that we would be nearly 30 years later and still using silicon. We thought it would die out by now, but you know, you just watch as people make new discoveries and push forward what turns out to be the best technology, and silicon's still by far the best in terms of being able to produce semiconductors in high volume. Yeah.
All right, one last question, and then we'll take the break. Go ahead.
I was wondering if the homogeneous computing choice from Intel, was that a convenience choice, or is that a matter of principle, or matter of financial motivation? And secondly, related to that, why not integrate small and fast cores with even more wider, bigger, and relatively slower cores, and put them on the same package, which is what would be ideal for many applications that don't fall in the category of massive linear algebra behind as a backend of some big compute.
Okay, so I think that there were two questions. One was about homogeneous versus heterogeneous, with an underlying assumption that somehow Intel's biased towards homogeneous, and wondering why. And then the second question was about, sorry, I've got to page these in. Give me a keyword. The second one was? Oh, big cores and small cores, yes. It was too fundamental to me. I forget quickly. Sometimes I have drawings that show big cores and little cores on the same die, and then I have a disclaimer saying not a product announcement under it. So let me address both. So homogeneous, heterogeneous. So first of all, homogeneous computing today is a myth. It hasn't existed for quite a while. In fact, I think last year when I was here, I think, Pete, it was you or someone that had a graph that showed some preliminary results at trying to run a tightly coupled program across the Sandy Bridge-based system, and how the cores ran at different speeds because of heat and so forth, and that the communication, that the performance of the machine went down as it got warmer. Because we don't cool machines to the same absurd levels. We used to super cool machines to make sure they behaved. Now we kind of warm water cool them and things. Even if you have a machine made up of all the same components, you start to get some heterogeneous. But you meant by heterogeneous different programming. So I actually think that as much as possible, the future of computing should be homogeneous programming on heterogeneous hardware. And I think it's I do not think that the future of HPC needs to be applications that are divided up and written in radically different ways, loosely coupled together. Now that's my hope. That's my stake in the ground, and part of the reason that I like the Xeon Phi project so much is that's what we're trying to cling to. Now, the reality is, though, acceleration things, application-specific acceleration, is always going to have an advantage from a hardware standpoint. A GPU is better at graphics. A CPU, in some places, if you're going to have a screen on your machine, you're going to have a GPU. Now, the question is on rendering. Yeah, on rendering, there are some types of rendering that are much better on a CPU than on a GPU, and some that are accelerated by the GPU. The reason is that the GPU encodes in hardware what it can do. And it's really good at what they did if the designers were any good, and they are. It's really good at that, but it's bad at what it wasn't designed for. CPUs try to be more versatile. So, but I think there's going to be a place for that, primarily because of power. The ability to build fat and wide things. One question I have is, do GPUs survive as, if you can build FPGAs, the sort of thing we're looking for in HPC, is FPGA a better question? I don't know. So yeah, I think the future is very complicated. I think your second question was, why not big cores and little cores mixed on a die? I personally believe that'll happen someday. I'm just not sure the market's ready to buy them in enough volume for us to build them and sell them today. And plus, we can only fit 72 Xeon Phi cores on a die right now. So it's if we put a Xeon core on there, we probably knock out, I don't know, 10 or 12 of those. So do you want a Xeon Phi with 10 or 12 less cores just because I stuck a Xeon on it? And you're nodding your head yes. A lot of people think that, and we'll see. I think that may happen in the future. It's not in our announced products right now, but I think it'll happen. There are a lot of people at Intel that think it will as well. I think it's a matter of when, not if. And the interesting thing to me is, well, if you're going to do that, what about slipping a little GPU on? What about putting a little FPGA on package, things like that? And then the question goes back to something you were asking before. Can you define a part that's still high volume? Or are you starting to get into one-off chips that are way too expensive to design and build? My hope is that with FPGA-style technology and stuff that we can make these things modular and that we can build them in the future. I do think the future is that. I think the future is heterogeneous computing and as much as possible homogeneous programming. And that's what we really should be aiming for, because the benefits of being able to have some versatility, some flexibility to the hardware designers to design different hardware is good, but I think that should not be the destruction of software. The software should have APIs and interfaces that we can program to that allow hardware innovation without requiring that the software be rewritten to every piece of hardware we come out with.